Hello, cosmic explorers, and welcome back. Today, we are embarking on an extraordinary journey, not to a distant galaxy, but deep into the very fabric of reality itself. We're going to tackle one of the most fundamental questions you can ask. Why does anything have? Why do you, the planet you're on, and the stars in the sky have mass? It might sound like a simple question, but the answer unlocks the secret to why the universe as we know it can even exist. So, let's start with a thought experiment. Imagine a universe without mass. What would that look like? It would be a chaotic, fleeting reality where every single particle, from the smallest electron to the most fundamental quark, would be a massless phantom. Everything would zip around at the ultimate cosmic speed limit, the speed of light. There would be no gravity to pull things together, no way for particles to slow down and coalesce. You couldn't form an atom because the electrons would instantly flee the nucleus. Without atoms, you can't have molecules. Without molecules, you can't have stars, planets, or people. It would be a thin, featureless soup of pure energy, devoid of structure, permanence, and life. That universe, in a very real sense, wouldn't be a universe at all. This wasn't just a wild thought experiment. It was a terrifyingly real problem for physicists in the 20th century. Their masterpiece, the Standard Model of Particle Physics, was incredibly successful. It beautifully described all the known fundamental particles, like quarks and electrons which make up matter, and the forces that govern them, carried by particles like photons. But it had one colossal, glaring flaw. The mathematics of the Standard Model predicted that, in their most basic state, all of these particles should be massless. This was in direct contradiction to what we observed. We knew electrons had mass. We knew protons and neutrons, made of quarks, had mass. Most damningly, we discovered that the W and Z bosons, particles that carry the weak nuclear force, were absolute heavyweights, nearly 100 times more massive than a proton. The Standard Model was like a perfect, beautiful car with no engine. It was incomplete. So, how did science solve this paradox? The solution came in 1964 from a stroke of genius, proposed independently by several groups of physicists, most famously including Peter Higgs, Francois Englert, and Robert Brout. They didn't propose a new particle at first. They proposed a new field, an invisible, all-pervading energy field that permeates every single cubic millimeter of space, from the vacuum between galaxies to the space between the atoms in your own body. This is the Higgs field. To understand it, let's use the most famous analogy. Imagine you are at a massive, crowded cocktail party that fills a huge hall. This party represents the Higgs field. Now, a person who isn't very well known tries to walk across the room. The partygoers barely notice. They part ways easily, and the person glides through without any resistance. This is like a massless particle, such as a photon, the particle of light. It doesn't interact with the Higgs field, so it travels freely at the speed of light. But then, a huge celebrity walks into the room. Immediately, partygoers cluster around them, wanting an autograph, a photo, a quick chat. The celebrity is mobbed. As they try to move across the room, this crowd of people moves with them, making it incredibly difficult to build up speed. They feel heavy. They feel heavy. This resistance, this interaction with the crowd, mass. A particle like an electron is a minor celebrity. It gathers a small cluster, so it has a small mass. A particle like the super heavy top quark is the biggest star in the world. It interacts intensely with the field, gathering a huge entourage, which is why it's so massive. This is the Higgs mechanism. Mass isn't an inherent property of a particle. It's a measure of how much that particle interacts with the Higgs field. So, if the field is the party, where does the particle, the Higgs boson, come in? Imagine someone at the door whispers a juicy rumor into the room. The party, the field, get excited and cluster together to pass the rumor along. This knot of clustered people, this ripple of excitement moving through the crowd, is the Higgs boson. It's an excitation, a quantum vibration of the Higgs field itself. Finding the Higgs boson, therefore, wouldn't just mean finding a new particle. It would be the ultimate proof that the entire mass-giving field is real. This is why it was nicknamed the God particle, a name many physicists dislike, because its existence is so central to the structure of our cosmos. For nearly 50 years, this elegant idea remained just that, a theory, a beautiful mathematical equation on a blackboard. To prove it, humanity would need to build the biggest, most complex, and most powerful machine in history, to shake the very fabric of the vacuum and see if a Higgs boson would fall out. We had the theory, a breathtakingly elegant solution to the mystery of mass. But in science, a theory, no matter how beautiful, is just speculation without proof. For half a century, the Higgs boson was the most wanted fugitive in all of physics, a goddamn particle, as Nobel laureate Leon Letterman originally called it, because it was so impossibly hard to find. The challenge was immense. How do you prove the existence of an invisible field and its fleeting particle? The answer? You build a cathedral of science, a machine powerful enough to recreate the conditions of the Big Bang itself. Welcome to CERN and the Large Hadron Collider, or LHC. The LHC is an engineering marvel that beggars belief. It's a 27-kilometer ring of superconducting magnets and accelerating structures buried 100 meters beneath the border of France and Switzerland. To achieve its power, its magnets are cooled by liquid helium to 1.9 Kelvin, which is colder than the vacuum of deep space. Inside this frozen ring, two beams of protons are accelerated in opposite directions. They circle the track over 11,000 times every single second, reaching 99.9999991% of the speed of light. At this velocity, their energy is immense. The protons are then guided into a head-on collision inside 4 colossal detectors, machines the size of apartment buildings, packed with millions of state-of-the-art sensors. So how does smashing protons find a Higgs boson? It all comes down to Einstein's most famous equation, E equals mc squared. Energy can be converted into mass and mass into energy. When two protons collide at such incredible speeds, their kinetic energy is converted into a blistering fireball. For a fraction of a second, the conditions inside that collision mimic the universe just moments after it was born. In that primordial furnace, a whole shower of new, exotic, and heavy particles can be created, particles that vanished from the universe billions of years ago. The hope was that, in a 1 in 10 billion collision, the energy would be just right to momentarily forge a Higgs boson. But here's the catch. You can never actually find the Higgs boson. It's monstrously unstable, decaying into other, more stable particles in less than a trillionth of a second. It vanishes almost instantly. So how could scientists possibly find it? They had to become cosmic detectives, looking for a very specific set of footprints. The theory predicted exactly what the Higgs should decay into. For example, it could decay into 2 high-energy photons or into 4 smaller particles called muons. The task was to sift through the wreckage of billions of collisions every second, looking for that exact telltale signature. This created a data problem of astronomical proportions. The LHC's detectors generate about a petabyte of data. That's equivalent to the data of 200,000 DVDs. It's physically impossible to store it all. So, incredibly sophisticated computer algorithms filter the data in real time, deciding in microseconds which 1 in a million collision is interesting enough to save. This filtered data was then sent to a global grid of tens of thousands of computers, analyzed by thousands of physicists worldwide. They were looking for a tiny bump in their graphs, a small excess of events at a specific energy level, indicating a new particle was being created and then decaying. It was like trying to hear a single specific whisper in the middle of a rock concert attended by everyone on Earth. For years, they searched. Finally, on July 4, 2012, the world's scientific community held its breath. In a packed auditorium at CERN, with a visibly emotional Peter Higgs in the audience, the leaders of the two main experiments, ATLAS and CMS, presented their results. They showed the graphs, and there it was. A clear, unambiguous bump at an energy of around 125 giga-electron volts. They had found it. The room erupted. Decades of theory, billions of dollars, the ingenuity of thousands of minds, and the construction of the most powerful machine ever built had all culminated in this one moment. The standard model of particle physics was at last complete. The discovery wasn't just the final chapter of a long search. It was the key that unlocked a new, deeper understanding of our universe, confirming that we live in a cosmos governed by a sublime, invisible field that gives substance to reality itself. What do you think is the next great mystery particle physicists should be hunting for? Let us know in the comments. Subscribe for more mind-blowing science, and see you soon.